Here's a puzzle. A plane flies in the sky, you are standing on the ground, listen and hear this. The tone of the sound kind of goes lower and lower. The question is, why? And I imagine some immediate responses would be like this.
I'll give you a hint. I'm the Doppler effect.
Indeed, just like a car, a bike, or whatever vehicle Sheldon was channeling, the plane catches up with the sound that it emits forwards and runs away from the sound that it emitted backwards. So the sound of the approaching bike or plane
is in a way compressed, which sounds more high-pitched, and the sound of the receding bike or plane
is stretched
and sounds a bit lower.
That's the Doppler effect. And at the first glance, that's exactly what we hear in the puzzle, the Sheldon's "ew" of the plane passing by. But let's hear it out till the end, shall we? How weird, the pitch of the sound goes back up. That's not what the Doppler effect sounds like, so what's going on? Let's examine the sound more closely. A great tool for analyzing sound is its spectrogram. It shows how much of any given frequency, that is, tone or pitch, there is in the sound. These examples should get across the idea. Now let's look at the sound of our plane. We see peaks and gaps moving in sync with the pitch, so it's probably them that we hear. The peaks and the gaps alternate with equal intervals. There is a certain base frequency that is cancelled out, double that frequency is amplified, triple is cancelled, and so on. And exactly that happens when the sound gets mixed with its echo with some delay. You see, if the sound matches with its echo, they add up to a louder sound. If the echo is opposite of the original signal, they cancel each other out. So when the frequency makes an odd number of wiggles, flip-flops, sign changes during the delay of the echo, it's gonna be cancelled out by the echo. And those frequencies with even number of wiggles will have the original and the echo sound perfectly synced, so they add up, combining their amplitudes. So we hear an echo of a plane. Okay, well, where does this echo come from? To get a hint, we can measure this delay. The first peak, the first frequency that completes one full oscillation during the delay, is at 100 Hz. That is, one oscillation takes 1/100th of a second. So that's our delay. Sound travels about 3 meters in that time. Where could the echo pick up these few extra meters? With the plane miles overhead, the only wall close enough is the ground. Thus, we got an alternative explanation on our hands. What we hear is not the result of Doppler effect, but that of the overlay or interference between the direct sound from the plane and its echo or reflection from the ground. Let's see how it holds up to scrutiny. First of all, does this mechanism change the tone the way we heard it, that is, the pitch going down when the plane is overhead and pitch going up when the plane is far, regardless of its direction? Well, the key frequencies are governed by the delay of the echo, which is itself determined by how much longer the echo had to travel. To compare the direct path to the echo, let's straighten out its path by sort of reflecting the reflected path back under the ground where your reflection hears it. We see that the extra mileage equals to this side of this right triangle. And playing around with it, we see that indeed this extra gap is longest when the sound comes right from above, and that gives longer delay and lower pitch, and shortens for the planes that are closer to horizon, whether they are approaching or receding. So at least that checks out. Alright, at least theoretically our explanation seems to work. But how can we know for sure? Maybe it's, I don't know, not an echo happening near us, but near the plane, reflecting from, I don't know, its wing, or something else entirely. Well, let the theory make a novel prediction and see how it fares. What can we tweak here? We cannot change much about the plane, but on our end we are in total control. For example, we can change the extra mileage for the supposed echo, for example by sitting down. And the tone of the sound should follow our movements. And It does, which validates our model. And to check out this effect, you don't even need to wait for a plane to come. A friend making a psh sound at a wall would work as well. Notice how the psh sound changes when you move back and forth against the wall. And bringing the source closer like that has a funny perk. It basically makes it the classic double slit experiment. In the double slit experiment, a wave passes through two adjacent slits, so they become new wave sources. Waves from both slits overlap and either cancel each other out or add up, depending on the relative lag between them. That should sound familiar by now. In the end, one sees a stripy pattern on the screen behind the slits. And in our settings, the slits are the pshing thing and its acoustic reflection in the wall, and we walk along the screen perceiving the interference pattern. There is a difference though. In the double slit experiment, there's usually a single frequency involved or close to that, so there are clear peaks and gaps in the pattern. To mimic that, we could also use one frequency, I guess by whistling, but then the interference pattern would only be audible as bumps in loudness of a single tone, and that is quite harder to pick up than the general tone shift across a broad range of frequencies, and to get a broad range of frequencies we use the psh sound, that is kind of like white noise. So, to summarize, in the classic double slit experiment, one sees the interference of a single frequency. And in our acoustic version, we hear the interference over the whole spectrum of frequencies, but at one position at a time. And this contrast between a single frequency and the broad spectrum leads me to my final remark. You may have carried along reasonable objection that, well, this acoustic interference model is fine and all, but the Doppler effect is still a thing, so where did it go? Why don't we hear it? Well, it would be that easy if your ears had a distinct frequency to grab onto, the ew instead of the shh. That is quite hard to pick out behind all that interference patterns. But when the plane is low, one frequency actually may stand out, leading to a weird sound that seems to go down due to the Doppler effect, while its texture goes up due to the echo delay shortening and interference pattern going up. To recap, the familiar sound change of a plane flying by is often not the familiar Doppler effect that you would expect, but rather the interference of the direct sound from the plane and its refraction of the ground, whose delay varies as dictated by the direction of the incoming sound. The best way to tell these effects apart is to change the distance to the reflecting surface. Interference effect will change tone in lockstep with your movements. This interference is basically a double slit experiment with slits that are far apart, and the main difference is that in double slit experiment we tend to see the whole screen but use only one frequency, while with the plane we hear a whole range of frequencies but only at one point at a time. I hope you find these surprises of the mundane event with parallels to this often mentioned but rarely observed first-hand physics just as fascinating as I do. Thank you for watching.